Buenos dias, my name is Tamás Szabolics. I work as a development engineer here at the Fusion Plasma Physics department of the Center for Energy Research. And today I'm gonna tell you about the fusion energy research. What is it? Where are we now? How can we make it on Earth? And what are we doing here related to this worldwide project? So let's jump right in. It is an old dream of mankind to bring down the sun to Earth. Researchers have already discussed the possibilities how to make it here on Earth in the 1920s. And now, 100 years later, the humanity is building the first reactor-sized fusion experimental device called ITER. But don't rush that far yet. Let's see what is fusion and how can we make it here. Fusion is the process when two light nuclear fuses and releases a huge amount of energy. To make fusion happen, the matter has to be in plasma state, which is the fourth state of matter and also the most common one in the universe, because 99% of the universe is in plasma state. For example, if we look at the night sky, all of the stars and also our sun are huge plasma spheres. Surprisingly, the sun has very low efficiency, because 1 cubic meter of sun matter only produces 1 watt of power, which is equals to 1 small LED bulb. So we have to make a little bit different kind of fusion here, which is more efficient. On Earth, the simplest fusion reaction we can make is the deuterium-tritium fusion. Deuterium and the tritium are the two heavy isotopes of hydrogen. In deuterium nucleus there is an additional neutron to the proton, and in tritium there are 2 additional neutrons to the proton. So these two fuels are practically abundant on Earth. Fusion is environmentally friendly because there is no CO2 emission, and also safe because there can't be any chain reaction related accidents. But it's not that easy thing to do here, because here on Earth we need 150 million degrees Celsius to make fusion happen, and also a suitable container where we can handle this hot plasma. In plasma state, the electrons are separated from the nucleus, which creates an electrically charged soup which can interact with the magnetic field. So if we put our plasma into magnetic field, it will float, so we can separate it from the environment. The device is capable of doing this, has a shape of donut or a so-called torus. And if we put magnets around the torus, this is called a tokamak. So we can float our plasma in the middle of the device, but it is not touching the walls. The other tricky part is how can we heat it up to the 150 million degrees Celsius. There are few ways to do it. One way is the microwave heating, which is quite similar to the regular microwave ovens, just 10,000 times stronger. The other way is neutron atomic beam heating, which can be imagined like a laser beam in some sci-fi movies. While microwave heating can heat our suit up to tens of million degrees, the neutron atomic beam heating will heat further up our plasma to the desired 150 million degrees. And now we are at the stage where we are building the first reactor-sized fusion experimental device called ITER. ITER is under construction right now in southern France in collaboration with 7 partners, including the USA, the European Union, Russia, India, China, South Korea and Japan. This device is one of the most complex scientific experiments in the history of mankind, and it will start operating 2025, the earliest. It will be the first fusion experiment which I hope will prove that we can build fusion power plants on Earth. It will produce 10 times more energy than it needs to run the experiment. We are also working on various tasks for ITER, but the most recent and complex one is a launching system, which is like a fire extinguisher, aims to shoot little hydrogen ice bullets called pellets into the plasma to prevent any malfunction causes possible damage to the device inner walls. This is a critical safety system, and we are developing the prototype version for ITER. Also recently, the JET experiment in the UK, which is the largest working tokamak right now in the world, achieved a fusion energy record using deuterium and tritium fuel. This was the first experiment using the actual fuels which will be used by future fusion power plants. And also there were significant Hungarian contributions to this project. GT60SA is a joint EU-Japan project which will start in autumn. For this, we developed and installed a video diagnostic system which will monitor the whole tokamak interior, and now you can see an image made with our camera after the installation. Wendelstein 7X, which is the largest tellurator in the world, which is another type of fusion device, will start operating this autumn after an upgrade. We have a 10-camera video diagnostic system there, with which we can see the whole interior of the device, and you can see actual footage made with our cameras right now. Hope you like this short intro into fusion research and where are we now. You can follow this research in the following websites and also on our social media pages. See you! Hasta luego!